Hello students, we're now going to begin a chapter on gases, the physical state that we sorta understand. And before we begin, a little mood music about gases. Okay, it's a gas. So, a chapter on gases. But first, let's talk about pressure. What is pressure and how do we measure it? Pressure is defined as force per area. Force per area. Well, how do we understand force per area? Well, consider a brick, a rectangular brick, and I have it shown oriented in two ways. And let's say we place it on a table. One, we lay it flat, and the other we have it on its end. In both cases, the force is the same because it's the force due to gravity, mass times the gravitational constant, g. But in the first case, that force, that weight of that brick, is spread over a larger contact area between the brick and the table on which it's laid. Whereas in the second case, the same weight, the same force of gravity, the same mass, but because that weight is now distributed over a smaller area, the effect is that it would be applying a greater pressure to the table. So pressure is force per unit area. Now the standard unit for pressure is the Pascal, PA, which is equal to a Newton per meter squared. Newton is a measure of force, and of course meters squares would be a measure of area. But in chemistry, we will more often measure pressure using other units such as atmospheres, torr, millimeters of mercury, even pounds per square inch, or possibly bars. So that's the definition of pressure, and a little later in one of our following lectures, we'll talk about the kinetic theory of gases and how this pressure is actually due to the molecules striking the surface of the container. But how do we measure pressure? Well, this goes back to Evangelista Torricelli, who invented what is called the barometer in 1643. And basically, it's a pretty ingenious instrument. This is how it works. This is what is called the mercury barometer. It's a long, skinny tube closed off on one end. The tube has to be a yard or longer. You close it off on one end, and then you pull a vacuum to one end and hold the tube standing vertically, and then put it in a dish filled with liquid mercury, and then remove my thumb from the open end, and what will happen? The liquid mercury will flow up the tube to a certain height, and then it will stop at some point. It will stop when the force of gravity balances out the atmospheric pressure. This will happen when the mercury has risen 760 millimeters, which is about 30 inches, in this tube. Now, if the ambient pressure happened to be higher, the mercury would climb up higher. If the ambient pressure was lower, it would climb up lower. So that's an instrument for measuring ambient pressure. And it is the basis for one of our units of measuring pressure, which is millimeters of mercury. So 1 atmosphere is equal to 760 millimeters of mercury. Now, because Evangelista Torricelli invented the barometer, we also call a millimeter of mercury a torr. So we also say 1 atmosphere is equal to 760 torr. Now, back to the pascals, 1 atmosphere is equal to 110,300 325 pascals, or 101 kilopascals. That's a unit we will not use very often. Even more frequently, we might refer to pounds per square inch. How many of you know that 1 atmosphere pressure is about 15 pounds per square inch? Well, I bet you know the pressure in the tire in your car, because maybe you have to check the pressure in the tire of your car every once in a while, and you find it's maybe 30, 32, 34, 32, 34, what? Pounds per square inch. So, that means that the pressure inside a tire of my car is maybe a little more than 2 atmospheres. Because if it was 1 atmosphere, it'd be about 15 pounds per square inch. So it's about 2 atmospheres. Okay, makes some sense. So those are units of measure of atmospheric pressure. Now, oftentimes what we will want to do is measure the pressure in one container and compare that to atmospheric pressure. To do this, we use what is called a manometer. And the bottom right-hand side of this slide shows a manometer. It is essentially a U-tube, filled again probably with mercury or some other dense fluid. Mercury works well. One side of the manometer is open to atmospheric pressure. That would be the right side, where we have what is called P0, or the ambient pressure. The other side of this container might have a cork, which is then connected to some other container which contains a gas at some unknown pressure. When we connect this, if the pressure in the unknown container happens to be also equal to atmospheric pressure, what would happen to the level of the mercury? Both sides, or both arms of this U-tube, would be equal. But if the pressure inside the unknown container is greater, it would push down compared to the atmospheric pressure, and you'd have a difference in the height of the two sides, h. And of course, if the pressure inside the unknown container is less, it would press down less, and you would have the opposite difference in the height of the two sides. So by comparing the height of the two sides, you can compare the pressure inside some sample in some container to atmospheric pressure, a manometer. Now on to some gas laws. I'm sure you anticipated that this chapter we would have lots of equations. The first gas law we'll talk about is what is called Boyle's law, after Robert Boyle, an Englishman. Boyle studied the relationship between pressure and volume. You can imagine that he had gases in some kind of cylinder device, and he would apply pressure, squeezing down, and measured the relationship between the applied pressure and the volume inside a container. And he found that volume is inversely proportional to pressure. And this is my first equation. Or you could say it this way: pressure is inversely proportional to 1 over volume. You can also rearrange this to say the product of pressure times volume is equal to some constant, which we'll call it CB, B for Boyle's. If you have a certain amount of gas, a certain number of moles of gas, under two different conditions, condition 1, condition 2, where these are pressure and volume condition 1 and pressure and volume condition 2, then the product of P1 times V1 is equal to P2 times V2. This would be a case, for example, if you have a gas in a container, like in a cylinder, and you begin with one pressure and one volume, and you either squeeze it down or decrease the pressure so that you go to a different volume at a different pressure. P1 V1 is equal to P2 V2. Next equation is what is called Charles' law, after Jacques Charles, a Frenchman who was a balloonist, who studied the relationship between volume of a gas and temperature. And he found that the volume of a gas is directly proportional to temperature, which you could also express as volume divided by temperature is equal to a constant with a subscript C for Charles. And again, if you have a gas under two different conditions, two different temperatures, the relationship that would hold would be V1 divided by T1 is equal to V2 divided by T2. So in other words, if you have a gas in some container, say a balloon, at one temperature, and then you change the temperature, if you increase the temperature, the balloon would expand. If you decrease the temperature, the volume of the balloon would decrease. Now, an interesting result of Charles' law is illustrated in the diagram that I just exposed. And this shows the volume of a gas measured over a wide range of temperatures. The numbers are hard to see, but I'll point at 100 degrees centigrade, 0 degrees centigrade, minus 100 degrees centigrade, minus 200 degrees centigrade, getting cold, and extrapolating as low as possible. And the point is that if you take a sample of a gas and measure its volume as a function of temperature, going as low as you can, you would extrapolate to, what do you think? What would be that lowest temperature at which all of these lines would intersect? These are lines for different starting pressures of gas, or different amounts of gas. They would all extrapolate to absolute zero, minus 273 degrees Kelvin. Interesting experiment. The third equation we'll talk about is what is called Avogadro's law. Yes, the same Amadeo Avogadro. Avogadro's law says that volume of a gas is directly proportional to the number of moles of a gas. V is proportional to N, which you can express in another way as volume of a gas divided by the number of moles is a constant, or V1 divided by N1 is equal to V2 divided by N2. Now, three separate equations. Why don't we put them all together? Great idea. If you combine these equations, we get, drum roll, what is called the ideal gas law. Pressure times volume is equal to the number of moles N times some constant, R, which we'll get back to, times temperature. This embodies both Boyle's law and Charles' law and Avogadro's law. You can see the components. Pressure times volume is equal to constant. Volume is directly proportional to temperature. Volume is directly proportional to the number of moles. So each of these equations is really embodied in this one larger equation, the ideal gas law. Now, in this equation, pressure must be in atmospheres. Keep in mind, it must be in atmospheres. Volume must be in liters, and temperature must be in Kelvin. N is in moles. You expected that. And then R is a constant, which we call the gas constant. Now, I've shown you in the slide the numerical value of this gas constant. R is equal to 0.08206 liters, atmospheres divided by moles per degree Kelvin. Before reflecting on that gas constant, let me point out something to you which is very, very interesting about gases. If you have 1 mole of a gas, and it could be neon or oxygen or carbon dioxide or hydrogen gas or helium gas, virtually any gas, if you have 1 mole of that gas, and if the pressure is 1 atmosphere, and if the temperature is 270 degrees Kelvin, the volume occupied by that gas will be 22.4 liters. For almost any gas, somewhere a little bit more, a little bit less than 22.4, but essentially 22.4 liters is the volume occupied by 1 mole of gas at 1 atmosphere pressure and at 273 Kelvin. Now, if you can remember 22.4, how big is that? Well, that's like 3 basketballs. It's 22.4 liters, or it's about the volume inside of your microwave oven. But if you can remember 22.4 liters and 1 atmosphere and 273 and 1 mole of gas, and plug those numbers into the equation PV equals nRT, you can solve for R. And you would find that the R would be 0.08206. The point is, you either have to know 22.4 liters as the volume occupied by 1 mole of a gas at 1 atmosphere pressure and 273 Kelvin, or you need to know the gas constant, 0.08206 liter atmospheres per mole per Kelvin. These are essentially the same information about gases, either the volume under those conditions or this gas constant. But it also tells us something interesting about the way gases behave, as we will see as we go through these lectures. We'll stop at this point, and then in the next slide, we'll talk about some useful relationships involving gases. We'll talk about partial pressures and how we can incorporate this equation, PV equals nRT, into stoichiometric problems with gases, etc. See you shortly.